My talk is devoted to obtaining stability regions for crystal lattices in straining space. I considered only 2D lattices in this work, and there are simple lattices like triangular and complex, for example, graphene. And I try to use molecular dynamic simulation to obtaining stabilities and instabilities and find what type of instabilities is realized. So there is pair interaction potentials, for example, Leonard-Jones and Morse potential. And in molecular dynamic simulation, I use Verlet algorithm to integrate equations of motion, this one, and temperature is considered as the average kinetic energy of the particles. So it's one of the stability criterion. I will talk about it later. And this is deformation of vectors which connected particles. So for simple lattice we have only this part, deformation gradient on initial vectors. So if we exposed a lattice by homogeneous strain, we will obtain another equilibrium state, and we not needed to solve equilibrium conditions which is needed for complex lattices. For example, this is Xi is shift of sublattices, and if we considered rotations, C is rotation of sublattice, particle in sublattice. So it's part of simulation, and we made triangle lattice with periodically boundary conditions, and expose lattice and boundaries by strain. After that, added some very small kinetic energy to considered instabilities in a, how to say, zero temperature. So if we tension lattice in, for example, one direction in X, we will obtain instabilities by cracking mostly. But if we compress lattice, we will obtain some other instabilities. For example, this is stability regions in strain space X, Y, and for example, in big compression, we will obtain randomly mixed material. But if in particular points we could obtain some group shifts of particles, so it's became another structure and structural transformation.
Good question.
Yeah.
For example, is epsilon 1 with extension?
Yeah.
This extension.
0 is nearly here. stress-free configuration.
So this is in the principal strengths?
Yeah.
So, principal strengths.
Yeah. And color shows amount of time steps to reach unstable configuration. So if we compressed sample, the time step which is needed to calculate is decreased dramatically. So it's not really time, but time steps. And this one is triangle lattice. This is triangle lattice which is rotated on P popolam, P divided by 2. And this is some called nearly quadratic lattice.
Just one more question.
Yeah.
I mentioned that the units on the axis are different in epsilon 1, epsilon 2.
Yeah.
Why? So this is a bit confusing. Why is that? And do you work with large strengths?
Yeah.
What is the strength measure that you use?
This is
Many strengths that you
not percent, but
Yeah, there are various strengths that one can choose. So what is it the large strength up to 1, right?
yeah, about 100% of extension.
Lagrangian?
Lagrangian. Next, this is work presented by Dr. Podolska, and in this work considered stability criterion as wave omega must be a real number. But if we considered instability, we can obtain for the condition is for all wave vectors. But if instability is realized on separate wave vectors, for example 1 or 2, it will be the new configuration and structural transformation, which we obtained by microdynamic simulation. And this is comparison between molecular dynamic red dots and theoretical investigation blue dots. So it's fully agreed. In this case, we tried to simulate instabilities for material with defects. It's quite simple. Defects with another potential well dots only. And the interaction between defects and normal particles is average from the interaction. In this case, if we deform sample, we will obtain unequilibrium configurations. So it's one of the problems. And the second problem is it's mostly problem. So the kinetic energy will looks like this for unstable configuration. The first part is transmission from initial configuration to equilibrium, and next, if we have the next maximum, so it's unstable configuration. And this like this is comparison between stability regions for ideal and non-ideal triangle lattice. So next we try to use moment potential proposed by Professor Ivanova, which considered three particles which is placed in ideal triangle, and each particle interact by Lennard-Jones potential, for example, or another pair potential. So if we expand in series interaction of the particles, it can be obtained potential which look like this, and angle is placed here. So for this type of lattice we need to solve equilibrium equations for sublattices shift, for sublattices rotation, and after that can be done some experiments. But unfortunately the results of experiments have mistakes, so that's all what I did. Thank you.
We have time for questions. No questions. So these are the defects you have what? Vacancies, or they are defects?
These another atoms, another type of atoms. Another type of atoms, defects. Yeah?
Which kind of instability I missed you find? Which kind of
there are many types of stability. For example, for tension it's cracks, so sample is destroyed. And for compression it's, for example, amorphous material, or if in particular points it can be structural transition. Yep.
Yes, you first and then go ahead.
You consider the expansion excellent. Actually, you generate all the terms. I did it for different shapes of bodies. You can have the series. This information related to the results of the stability.
In which? In momentum interaction?
Both
Yeah.
When you expand it in epsilon, can you take into account how much terms? The first two terms, no?
Yeah, it's first two terms.
It's possible to write down all the...
Yes, I think it's will be needed for more strong interaction. More strong.
You think that if you translate it doesn't influence the results of the stability?
For mostly pair interaction, no. So it's.
From the computational point of view, which is the cognition data check to establish that there is instability at a certain time step?
We saw in kinetic energy, and if it not reach the for ideal lattice, if it not reached the initial level after the calculation starts, so it's stability. And we can choose initial energy as small as we want, so it's very stable configuration for little oscillation.
All right, well, thank you so much. I think this is the appropriate time to thank the organizers for an excellent, invigorating program that they